All right. Hello, everyone. Thanks for introducing me, Pavel. I'm Nitin Bhat, and I'm a software engineer at Charmworks. And I'll be giving this presentation along with my colleague, Jaemin Choi, who's a PhD candidate at the University of Illinois, Urbana-Champaign. So I'll be giving the initial updates over the last 1 year of Charm++ and UCX, and Jaemin will be talking about a specific feature that he's working on related to Charm++ and GPUs, and more about that and how that ties with UCX. So this is the outline of my talk. I'll be initially giving an overview of Charm++. For those of you who don't know, in last year's workshop, I mentioned more about the underlying details and the implementation. So this time I'll keep it brief. And I'll also then talk about Charm++ and UCX and the brief history of what has happened over the last 1 year or so. And then some bugs that we dealt with on this machine Frontera from TAC, which was basically most of last year, but luckily they're fixed now. So following that, I'll be talking about some very exciting results from NAMD that we got recently. And finally, I will conclude and talk about the future directions that we can take. So let me start off by giving a brief overview of Charm++. So Charm++ is a generalized approach to writing parallel programs. So it supports both distributed memory and shared memory parallel programming models. So it's similar to the likes of other parallel programming approaches like MPI, UPC, global arrays, but it's not a sequential language like C or C++. In fact, Charm++ is based and written on top of C++, and every Charm++ program is a C++ program at the end of the day. So there are three key design principles in Charm++'s design, which are like the central ideas. Let me briefly go over each of them. So the first one is over decomposition. So over decomposition means basically decomposing your work and data into more number of units than the number of execution units that you have. So typically, like in MPI, you decompose the domain such that you have one rank per processor element or core, but in Charm++, you do the decomposition, you just overdo it. So typically you have about tens or 20 of these entities, which are basically C++ objects residing on each processor. So that is the meaning of over decomposition. The second central idea is migratability, that each of these entities can be migrated from one processor to another processor during runtime. So what this basically means for the application programmer is that the entire application logic is written in the form of logical indexes rather than the physical processor. So if an object, say the 23rd object wants to talk to the 63rd object, you use a global handler and directly address the 63rd object, irrespective of which processor it's living on. So what that means for the runtime system is that the runtime system determines where the 63rd object, which is the receiver, is living on, and make sure that the message is sent to the right processor. The third design principle is asynchrony. So asynchrony is to basically deal with the question of who gets to run next. So you have these multiple C++ objects spread across different processors, but who will run next is answered by the answer to that is basically whoever has a message ready for them. So each of the processors have a scheduler which enqueue messages, and the object or the C++ entity that I mentioned, which has a message next, is the one that basically runs next. So each of these objects talk to each other using these asynchronous method invocations, which are essentially like function calls, but just that they don't wait for the return like typical function calls. And another property is that they have like a global address space. So I can invoke any remote function that is basically targeting an object that is on another processor. So these three key design principles allow us to do interesting things and enable features like automatic overlap of computation and communication. and load balancing, which is a very key feature of our programming model and runtime. So using the design principle of migratability, these small objects can be moved from the overloaded processors to the underloaded processors, and then you can balance load and get better performance. Another feature is shrink and expand, which basically is for resource elasticity. That is, during runtime, I can reduce the number of cores or nodes by moving the objects on the processors to the other processors. And another feature is fault tolerance. By using a checkpointing scheme, the system can be made resilient, where in the event of a failure, the simulation can be restarted on from the previous checkpoint by resurrecting the objects from another checkpoint on the other processors that are still alive. So these are very key features and especially relevant in the era of exascale computing. So when I say Charm++, to summarize, it represents the style of writing parallel programs, which is the parallel programming model itself, where you represent your entire application in the form of these bunch of interacting objects that talk to each other with asynchronous methods. And it represents the introspective and adaptive runtime system that allows us to measure load and balance whenever required. And it also represents the ecosystem of tools and libraries that support it. So this involves tools like the visualization tool called LiveViz. There's a performance analysis tool called Projections, and also libraries like Adaptive MPI, which is an MPI implementation on top of Charm++, and then collision detection library and a few other libraries, to mention a few. So moving on to Charm++ and UCX and a brief history of it. So Charm++ was initially developed at the University of Illinois Parallel Programming Laboratory, which is Dr. Sanjay Kale's research group. And that happened in the early 1990s. And recently, since about 5 years, it's been co-developed by Charmworks, which is a startup that commercially supports and licenses Charm++. So as and when new machines have been installed and whenever Charm++ was used on them, we roped in and created new machine layers or communication layers, starting off with net LRTS to MPI, and then native layers like GNI, verbs, and so on. So why did we need a new communication layer? So for the new class of InfiniBand machines, verbs was not working very well. And it was also difficult to maintain since it was quite a dated layer that was not maintained very well. And MPI layer, again, was a layer that was written early on and was not scaling very well, especially in the SMP mode, which is the one that enables shared memory optimizations. And UCX library seemed like it had support for a lot of backend networks and hence offered portability and high performance and seemed like it was easy to maintain. So that's why it was a decision to rope in and develop a UCX backend networking layer for Charm++. So in June of 2019, the UCX networking layer was added to Charm++, primarily by Mikhail from the UCX team, along with some others from Charmworks and UIUC. And it was added to the nightly build starting July 2019, where both the SMP and the non-SMP versions were tested against our entire test suite. And now, since I think a couple of months, it's also been, the UCX targets have also been added to a part of our continuous integration where it's tested against each patch that we submit on GitHub. So the initial performance results were very exciting. And this, I think, largely had to do with the fact that the original layers that we were comparing UCX against were not performant, not that performant to begin with. So for ping pong, we saw a 67% better improvement over MPI. And for verbs, we saw almost up to 87% improvement. And NAMD, this was one of the first experiments that was performed on 22 nodes of Thor. We saw that it performed about 4% better than MPI. And Changa, in the cases where it ran successfully, it showed about 37% improvement over MPI. And these were initial tests that we were very happy with. However, in November 2019, I think it was during one of our BOF sessions, we saw that one of our application teams, which was this cosmological application called ENZO-P, was complaining about these hangs and crashes that they were seeing on Frontera. And since then, we basically were involved with a lot of debugging efforts of these bugs that we saw on Frontera, and they were finally fixed in September 2020 in UCX 190. It was fixed in the release candidate, and we saw it rolled out in the release. But I think earlier that year of this year, we could use the master branch, and our application teams could get on with testing and development of that. So I'll be primarily focusing from this point on the bugs that we dealt with, because that was where most of the year from our end was spent. So talking about the Frontera bugs, as I mentioned, initially it was the ENZO-P application that that did not hang consistently. It was inconsistently hanging on 4, 8, and 64 node runs. And we saw that as the node count increased, the number of jobs that hung also proportionally increased. And a similar observation was seen with NAMD for one of the Zika virus simulations, which in the SMP mode hung for 16 node runs. And this was fairly consistent. Every time we ran it, it hung. And Changa as well was seeing crashes on 32 and 64 node runs, and sometimes hangs during load balancing. So this was a very tricky bug because because the hang couldn't be reproduced with any of the simpler test cases we had. We even reproduced some other benchmarks, like a bombard benchmark, where you basically bombard one of the receivers in an all-to-one, and in some cases all-to-all fashion with a lot of small messages. So even those test cases couldn't reproduce this bug. So it was a very tricky bug in that sense. And it couldn't be seen on other machines as well, like Golub and Thor were some of the other machines we tested. And I think Mikhail tested Helios and some of the other machines in HPC Advisory Council, but it could be only seen on Frontera, which made us believe if there was something weird about the machine, since it was up and coming as well. We also tried other layers like MPI, since we have an MPI port on which Charm++ can be installed. We did not see any hang with Intel MPI, but for some of the custom built MPIs like MPitch and OpenMPI, we did see some hangs. But interestingly, looking back, these hangs were different from the hangs that we saw during UCX, because these hangs appeared right in the beginning, almost during the PMI setup. So it seemed like the processes were losing connection with the other processes. So it seemed like they were different hangs, but at that point we were clueless about them, and it still didn't allow us to run the application. So we made quite a few debugging attempts throughout the year. We had quite a few discussions with the UCX and NAMD teams about how we can tackle this tricky bug. And I think one of the attempts, I had discussions with Yossi and Mikhail in last year's dev workshop as well, where we tried getting stack traces from hung processes. And later on, when I tried this experiment again with a bigger run that hang, I basically saw that all the PEs were in Charm's idle scheduler loop. So since Charm has a scheduler that runs on every PE, if there are no messages, it's just an idle loop that keeps running. So basically this pointed to us that there's probably an issue with delivery of messages. That is, it's possible that there are some messages that are undelivered, and those are not allowing the application state to move forward, and that's why the hang could be possibly occurring. So we even reached out to TAC, and with the arrival of COVID-19, NAMD is a important application in determining structure of biomolecular systems, So it was important for COVID-19, and as it was important in the case of giving the structure of the HIV capsid as well. So NAMD's use became even more important. And we even got a special allocation on Frontera for debugging this bug. We also tried developing a message tracking infrastructure to see where all sent messages are going, whether they're all being received. So the implementation was fairly simple, and we implemented this in Charm, and any program could be run with this flag, which was track messages. So basically the implementation entailed for every message sent on the sender PE, you generate a unique tag and you store it in a map. And then once the message is received on the receiver PE, it could be the same PE or it could be another PE. By PE, I basically mean a core. PE stands for like a processor environment. So when the message is received on the receiver, an acknowledgement message is sent back to the sender PE. And when the acknowledgement message is received on the sender PE, the unique entry is removed because that basically signals a successful delivery. And when the application hangs, as we saw in the case of quite a few application runs on Frontera, we saw that during the in the scheduler loop, we have a timer that basically triggers a reduction to print out all the message entries across all PEs that were not ACT. So this allows us to find out all the undelivered messages. So running this with EnzoP showed us that there were a few unacknowledged messages on a few PEs. In some of the runs, it was only 2 PEs that were having entries, but in some of the other runs, I did see a few other PEs or cores having undelivered messages. When I tried it with NAMD, I remember that I think I couldn't replicate the hang anymore. So I was only successful in using this and getting undelivered messages with Enzo. So around the same time, I think I gave the UCX master a shot, and around June 2020 of this year. And that didn't show any of the hangs anymore, which was great. And it looked like the bug had been fixed. Since we were struggling with this, I did a git bisect on finding out, in attempting to finding out which commit caused the fix. And I think there was a crash in UCX arbiter that was showing up. So initially there was the hang, which we were dealing with in some of our applications. And then there was a crash. So my bisect could only take me to the commit that fixed the crash, but I was not successful in getting the hang. But it'd be good to find out from all of you if you know the commit that fixed this hang on Frontera.
So I did a fix on the arbiter in case that you have some sends which are happening from send callbacks.
Okay.
There was a crash in the arbiter when we tried to add things to the pending queue while its arbiter is being dispatched.
Okay. So your change fixed the arbiter, but is it the same change that fixed the initial hang?
I think that it's not the same
Okay.
one.
Okay. So yeah. So thankfully, in any case, it was fixed and it was a part of the release. So we could use it starting then. And it was quite a big relief because things could progress on with the NAMD testing. So moving on to more exciting news. So since we were able to use the UCX latest versions, we performed quite a few scaling experiments on Frontera. And this is one of the scaling plots of the satellite tobacco mosaic virus, and that's what STMV stands for. So the bottom set of plots here are for the 210 million atom system, and this is for the 20 million atom system. And you have nanoseconds per day on the y-axis, and you have number of nodes on the x-axis. So each node has, I think, about 50 odd cores. So this has scaled quite well to 512 nodes, which is about 28,000 cores. So we are very happy with this result. And it even got featured on HPC Wire. And this effort of NAMD scaled on Frontera, along with other scaling efforts on ORNL Summit, was a part of this multi collaboration effort from UCSD and ORNL and ANL and a few other teams. And they even won the Gordon Bell Award in this year's supercomputing for research on COVID-19. So that was a really good achievement. And thanks to the efforts of the UCX team for making this scalability happen. We also tried, and these plots are from the NAMD group and given by them, and the experiments were also conducted by them. So this was another scaling effort on Azure Cloud, where each node had 120 cores, and a similar plot of scaling the 20 million and the 210 million atom system. By the way, the 200 million atom system is apparently very close to the COVID-19 virus structure. So this also scaled pretty well to about 86,000 cores. And this is the scaling plot. The 20 million atom system does not scale quite as well, starting from 256 nodes, but nevertheless, it does scale pretty well. So talking about more Frontera bugs that still need to be fixed with Charm UCX, there is one of the bugs that I think Mikhail was looking into along with our collaborator, Tom Quinn, for Changa, which is this cosmological application. And it has a lot of short messages, which are sent in almost a bombardment fashion. And on Frontera, we are still seeing this issue of failing to register memory, which is for the pinned memory. And there is an open issue on the Charm GitHub, as well as a similar issue on UCX as well. And Mikhail, I think, also created an active messaging API port for Charm++, where instead of implementing it using the standard UCX send and receive function, he used the active messaging API, and that seems to be helping avoiding the registration up to 24 nodes. However, I recently just found out that the 2-node run is still crashing with the same error. So hopefully we can get that fixed, and that's one of the still big ticket pending items, because Changa has a big allocation on Frontera that they would like to use and run successfully. So hopefully we can get that fixed over the next couple of months. So in conclusion, I would like to say that most of the year was spent with the Frontera bugs, and they were very tricky and took a lot of time and effort from our end. But thanks to Mikhail for all his help over the year, which was very useful. And in those cases where we were able to bypass the bug, thanks to the fixes on UCX master, and in the recent version, we were able to scale quite well on InfiniBand machines, and as indicated by the NAMD plots that I showed you. So in future work, I would like to get performance results from other applications as well. Enzo and Changa would be the two big ones that were using Frontera, and we'll hopefully get good results from them, comparing them to MPI. And we also plan to use UCX on some of the other up and coming networks like Slingshot Interconnect. I'm not sure if there are plans to support that network as well, and as well as other older GNI machines like Cori and other PAMI machines like Summit. So that's the plan for the upcoming months. And in terms of features, I think I already spoke about Active Messages API, which is there is a patch in progress, so we would like to review that. And I think the active messages API fits more of the Charm model, because Charm at the higher level is essentially active messages where handlers are invoked as soon as a message is received. So that will be good to get integrated and compared with the current implementation of UCX, which uses tags and tagged sends and receives. And we would also look at the collectives API if it is mature and ready to use, and implement some of our broadcasts and reductions using the collectives API and compare it with our current implementation, which uses point-to-point largely. And we also are working on inter-GPU communication in Charm++, which will be the next talk given by Jaemin Choi, and he can talk more about it in detail. But that's all for my presentation, and I can take any questions.
Could you comment on the performance improvement of 87% when you moved from verbs to UCX? Because like at a micro benchmark level, they're pretty similar.
Right. So I think it was primarily the way the verbs layer was written. So it was quite old and it was not maintained. And we saw that many a times we ran into like issues with registration and stuff. So from my end, I think it's largely to do with the fact that the verbs layer was not maintained. So if experts can, if you guys can take a look at it and see if there are other ways we can resurrect the verbs API, I'm guessing that we can do slightly better. So, but to answer your question precisely, one of the things that was not in verbs but was in UCX was a registration cache. So that might have to do with a lot of the improvement that we saw for the larger messages.
Yeah, that makes sense. Thanks.
Hi, Nitin. Thanks for the presentation.
Hi, Mikhail.
I have a question about Active Messages API. So if we're going to proceed with it, are we going to keep tag implementation, or we will just replace it with Active Messages?
I feel if it solves the issues that we are seeing with Changa, and if we do initial performance results and it seems to perform well, I don't see a reason to keep the tagged version still around.
Okay, I agree here, because Active Messages is a better choice for UCX machine layer. But the reason we started with Tag API, because we didn't have all Active Messages API ready yet at that time.
Right.
And we will have it only in 1.10. So if we remove Tag API, Charm++ will work with UCX starting from 1.10 only.
Yes, that's a good point. So we can possibly, like, once after. So what's the expected timeline for the 1.10 release?
Yossi, Pasha, can you help me here? I think it will be somewhere in the beginning of the next year, right?
Okay. So in any case, I think what we can do is we can create a pull request on the tagged stuff, and we can do the initial performance testing. And after that, we can probably put like a macro where either of them can be switched out as required. I think having the option of both will be good. But I do see that it'll be good to have backward compatibility. So for that reason, I think we'll still have to keep the tagged version around.
Okay. So I think we will continue this discussion offline.
Yeah. I had a question about this, just to get, because we have spent so much time on the Frontera bugs, I'll be attempting to do a git bisect again, just to find out which change in UCX was actually causing it. So I might need your help on that one, Mikhail.
Okay.
Okay. In that case, I think, can one of you make Jaemin the presenter? I think he can continue on the presentation about Charm and GPUs.
Hi everyone. Thank you for having me. So my name is Jaemin Choi. I'm a PhD candidate at the University of Illinois Urbana-Champaign. And I'll continue the talk on Charm++ with UCX with a focus on inter-GPU communication. So just to start off with a brief overview of how the messaging API works in Charm++. So it's essentially a message-driven execution where objects that are potentially on different processors exchange data via messages. And when a message arrives on the receiver object, it will invoke a method that will use the received data and perform some computation. So in this example here, so we have two objects, the source object and the destination object. And the source object is attempting to send three separate buffers that are on the host memory. So one is just an integer, A, and the other two, B and C, are vectors of doubles. And they eventually will invoke the foo method on the destination object. So since the Charm++ messaging API supports sending multiple buffers at the same time, what we do is we perform a technique called parameter marshalling, where we allocate a separate contiguous buffer that can contain all the three separate buffers, and then we copy the original buffers into this contiguous buffer, which we call the marshal payload, and the diagram you see here. And then we combine that with some metadata that contains information that is necessary for message-driven execution, including the destination object ID as well as the registered method ID. So we combine those together as a message, and we send that over to the destination object. And when the destination object receives that message, it will unmarshal or unpack the message that will contain the metadata as well as the data buffers. And the metadata is used to invoke the correct method on the destination object, which is foo in this case. And also the destination object can access the received data, which is unpacked from the message. So building on top of this, we currently have a prototype implementation for exchanging data that's on the GPU. So this is currently built on top of the zero copy entry method post API, which is explained in more detail in this linked manual as well.
You would want to start it, or you can even change the fragment size.
Oh, okay, I see. Yeah, that'll be good to play with. Thanks.
Jaemin, can you go back to the previous slide?
Sure, this one?
Yep. So some preliminary questions. I may have missed a few details. So the Charm UCX case, the yellow line here, it's basically transferring GPU buffers between two processes. Is that right?
Yes, two processors that are in the same socket. Yeah, but different processes.
And you did say that, you know, the overheads do come from packing and unpacking here, right? And
right,
is
the
that
Charm++
something
versions,
that,
yeah.
and that's something that Charm++ explicitly executes, right? At the source and destination.
Right.
And what is the routine used to pack and unpack? Is it CUDA mem copies or is it some generic function?
Oh, so the packing and unpacking are just happening on the host side for the message that is exchanged between hosts. So that has the metadata and the data that has to be sent across host. That does not involve any data that's on the GPU. So there's no packing or unpacking for GPU buffers. The GPU buffers are sent individually using the UCP send calls.
Okay. So, you know, I was just curious to know if, you know, packing and unpacking implicitly involve CUDA mem copies and you were seeing the D2H and HTTP copies as a result of that. So that's not
right.
All of this is coming from UCX. Is that right?
Well, yeah, there are some like Charm++ overheads, but mostly from UCX, yeah, because the GPU data are sent using UCX. Yeah.
So with the NVProf results between 1 and 8 kilobytes, did you see D2H and H2D on the profile?
Yeah.
So that would mean that there's no GDR copy being used, and that would explain why the latency is higher, because once there's GDR copy, UCP would resort to using AMZ copy protocol, where it would directly register GPU buffers and place them on host bounds buffers on the receive side, and from there it would do GDR copy transfers. And there you should see significantly lower latency. And one of the reasons for this could be that Summit had been resistant to using GDR copy module, but I think in recently they have gone ahead and installed GDR copy module. So you may want to check in to see if that's installed.
Yeah, so I did check the services and modules. I think there's like instructions to check for that on the UCX documentation. So I did that on the compute nodes, and they seem to be running the GDR modules and the NVIDIA modules. So yeah, I'm not exactly sure why it's not using GDR copy here in this case, but yeah, still needs some exploration.
Okay, and can we go to the next slide? So Mikhail mentioned that there could be small fragments of 8 kilobytes being sent, and that could be the reason. I just wanted to comment that, Mikhail, do you think this applies even, this shouldn't apply to, GPU to GPU transfers, right? This applies only to hosts, as far as I understand. I know there's like a fallback protocol which ends up using an 8 kilobyte fragment pipeline, but in general circumstances, it should be the case that there should be just zero copy operations being used. Is that not right?
If I'm going to be true, I'm not sure. It needs to double check.
Okay.
Usually, I even thought that it's between two processes residing on different nodes.
Okay. I guess one test to run here would be to OpenMPI when built with UCX, pretty much uses what UCX is expected to do. So another comparison that you can run. So instead of running Spectrum MPI, you could run OpenMPI and UCX.
Yeah, that's a good point.
And see how NVProf it shows you there. And whatever you see with Charm UCX should be identical to that. And if not, then there could be an artifact in Charm plus that could be resulting in this difference.
So maybe it's because we start rendezvous protocol only from relatively large size, and the other MPI, the CUDA-aware MPI starts basically with rendezvous with 0 size.
Correct. On Summit, Spectrum MPI does start with almost 0.
Yeah, so I think that's the difference, because 10 looks like similar to rendezvous round trip.